Hello everyone, this is Dr. Shalini, Associate Professor, RMD Engineering College. In this video, you are going to look into interference. Interference refers to the superposition of two waves which results in a wave of greater, lower or the same amplitude. These are few examples of the wave interference. You see the soap bubble, which is a well-known example of the interference, and you have the interference of circular waves. Looking into the types of interference, there are two types of interference. They are constructive interference and destructive interference. When the two crests meet, or when the two troughs meet, it leads to constructive interference. A crest and a crest and a trough and a trough results in constructive interference with a higher amplitude. And a destructive interference occurs when the crest meets a trough or a trough meets a crest. This is the final input of a destructive interference. We see the condition for a constructive interference. This occurs for a bright fringe. When two waves are taken into consideration, the path difference is equal to an integral multiple of wavelength lambda. So path difference is equal to n lambda for the values of n being 0, 1, 2, 3, 4 and so on. So the path difference between two waves, if it's an odd integral of lambda by 2, it leads to destructive interference with a path difference of 2n minus 1 lambda by 2 or 2n plus 1 lambda by 2. The light interference is first being observed by Thomas Young in the year 1800 with an experiment of Young's double slit. Here we have a source. This is a single slit just with S1, and here we have two slits S1 and S2. The rays of light occurring from S1 and S2, as a result of overlapping, it leads to an interference pattern on the screen. Here we will now look into the derivation of the Young's double slit experiment. As you consider the screen XY, the point CP is given by the value X. The interference between the waves reaching the point depending on the path difference S2P and S1P can be obtained from this. As we go with S1P square, the value is d square plus x minus d by 2 the whole square. And the value of S2P square is d square plus x plus d by 2 the whole square. As you subtract both the equations, you will arrive at the value of S2P square minus S1P square is equal to 2xd. We have this in terms of a square minus b square, which is a plus b into a minus b. We have S2P minus S1P, and S2P plus S1P is equal to 2xd. As we know, the path difference is S2P minus S1P. We go with that term on this side and the other terms on the other side. which is equal to 2xd by S2p plus S1p. This value of S2p plus S1p is 2 times the value of d. So we have this S2p minus S1p given by 2xd by 2d. As discussed, the path difference which is obtained earlier leads to the value of the phase difference with the formula phase difference is equal to path difference into 2 pi by lambda. The obtained value of the path difference is xd by d, which results in the value of phase difference given by 2 pi by lambda into xd by d. So this gives the condition of the bright fringe as already discussed. For a constructive interference, it is an even multiple of lambda by 2, which gives the value of x is equal to n lambda d by d. Coming into the destructive fringes, it gives about the dark fringes with a path difference of an odd multiple of lambda by 2, which goes with the value of xd by d is equal to 2n minus 1 lambda by 2. So the above equation gives the condition of dark fringe or a destructive interference. As discussed earlier, the alternate dark and bright fringes can be obtained by the values xn minus 1 minus xn. On simplification, it leads to the value of d by d lambda. And for the dark fringes, the same value results in d by d lambda. Hence, the distance between the alternate dark and bright fringes remains the same, which is denoted by beta, the fringe width, given by the value d by d. Now let us look into what a Fresnel's biprism is. It's a double prism which is placed base to base. This is a single prism. This is just a prism. When two prisms are placed base to base, it refers to what is Fresnel's biprism. It has a very small refracting angle of about 0.5 degree and its angle is nearly equal to 179 degree. As we move into the application of Fresnel's biprism, it is capable of determining the wavelength of a monochromatic light as well as it is used to determine the thickness of a thin sheet of transparent material. With this, the determination of wavelength lambda of a monochromatic light using a Fresnel's biprism can be obtained, of which the conditions for maxima and minima are given by the formula delta is equal to n lambda for a maxima and delta is equal to 2n plus 1 lambda by 2 for a minima. Thank you.